Dane here for topic 8.7 pH and pKa. So our first question is, what are indicators and what do they do? So hopefully you've already gone through our indicator lab. And if not, hopefully you've gotten the pictures from a buddy and can kind of follow along with this. So indicators are something that change or pretty much tell us if something is changing or the presence of something. So in the case of pH indicators, it's telling us, so the color changes based upon the pH. And that color changes basically because of what happens with a hydrogen ion or a proton. So just to remind you, when something talks about protonated or deprotonated, it's talking about, like, if we say we have a hydrogen atom, we have one proton, let's say 0 neutrons, and it has one valence electron. If we remove that valence, if we make this an H plus ion, we just have a one proton, 0 neutrons, and we've removed that valence electron. So essentially, it's just one proton. So anytime that you see protonated versus deprotonated, it's talking about adding or removing hydrogen ions. So make sure we keep that in mind for this. So here we have two versions of bromocresol green. One is protonated and the other is not. So for this, you're going to try to find which one has that extra hydrogen and which one does not have that extra hydrogen. So we can take a look at the arrows. We have a negative H plus going in the right direction, meaning that this one removed or lost a hydrogen ion to become this one. And in the reverse direction, this one gained a hydrogen ion to become this version. So to find that hydrogen ion, it's going to be right here versus this one doesn't have that in spot. So with bromocresol green, it happens to change colors, and that's the same thing with all these indicators. They change color whether or not they have that hydrogen. So bromocresol green and will be a yellow when it's its protonated version, and it's blue in its deprotonated version. And the in-between, so the in-between between yellow and blue is green. So this one is the acidic or the protonated version. And this one is the basic or the deprotonated version. So bromocresol green's pH range is 4.0 to 5.6. Its pKa is 4.7. So explain the relationship between the two, between the pH versus the pKa. So if we know the pKa of this is going to be 4.7, that's that in-between section right here. So that's your pKa is equal to your 4.7. So again, it's that in-between region. And that pH happens to be 4.0 to 5.6. So that pKa falls in between the pH range. If we have something that's less than 4.0 and 5.6, it's its acidic or protonated or yellow version. If it's greater than 5.6, it's its basic or deprotonated version. So the relationship between the two is that the pKa falls in between its little pH range of changing color. So over here, you'll find table M, which is also part of the New York State reference table. Let's zoom in really well. Maybe. Okay. So essentially, this is showing us the change color, the range of changes. I want you to labeling it on your New York State reference table. This is just the one that I happen to have right here. If you don't have your New York State reference table with you right now, fill this in, and then we can do your table later on. So methyl orange, it's red anywhere below 3.1. And above 4.4, it's yellow. So I'm going to show that below or to the left of 3.1, it's red. to the right or above 4.4, it's yellow. So our in-between color is an orange. So at 3.1 to 4.4, it's going to be orange. Bromethymol blue, below 6.0 is yellow. Above 7.6 is blue. And our in-between color is green. And it's a gradual color change. I just am not showing that gradual color change with these colored pencils. Phenolphthalein, above 9, it's pink. So I'll just do a lighter color. And below 9, or sorry, below 8, it's going to be clear. So the in-between is going to be like a super, super light shade of pink. We can get that in there. All right, litmus. Below 4.5 is red. Above 8.3 is blue. And the in-between is a purple. Bromecrestol green. We did this one already. So below 3.8 is yellow. Above 5.4 is blue. And in between is our green. And thymol blue. Below 8.0 is yellow. Above 9.6 is blue. And our in-between is green as well. So notice we have a few that are green in the middle, but their pH ranges are different. So like bromethymol blue changes to is green at a pH range of 6.0 to about 7.6, whereas bromecrestol green is green at 3.8 to 5.4, and thymol blue is green at 8.0 to 9.6. So this will tell us like what might happen with all of these. So let's say we have, something that has methyl orange that's yellow. It's anywhere it's above 4.4. So it can be anywhere from 4.4 up to 14. So some things I want to show you with this table over here. If you didn't already get this, make sure that you do get this. So this is what we filled in during lab today. And this is just another visual representation of what we have seen in that New York State reference table. But this time I'm going to give you some pKa values. So the pKa, and maybe I'll squeeze it into here, for methyl orange is 3.4. So that means at around 3.4, and it's not precise, but around here, it's orange at around that 3.4. Anything below there would be red. I apologize for not coloring in the lines, but we want to go through this fairly quickly. And anything above there should be yellow. So even in lab, if we only tested solutions 2 through 11, you can still tell the other two extremes based upon what else is around there. Bromethymol blue, it's pKa 7.0, so that one turns green, 7.0. According to this table, it's yellow, anything below. And anything above should be blue. All right. So essentially, you should get these all kind of filled in. Let me give you the other pKa values while we're here, though. Phenolphthalein is 9.4. Litmus is around 6.5. Bromecrestol green is 4.7. And thymol blue is 1.65. Universal indicator, on the other hand, has a bunch of different pKa values, hence why it changed color more so than more than just the 3 colors. It had a variety of different colors. That's why it's more universal. Cool. So if we take a look down here, we're going to use the Henderson-Hasselbalch equation to help us figure out what happens between the pH and the pKa of our acid and our weak conjugate base. So to remind you guys, Henderson-Hasselbalch, the pH is equal to the pKa plus the log of the conjugate acid over the concentration of the conjugate acid over the concentration of, the concentration of the conjugate base over the concentration of the acid. Phew. So let's just make sure I have this in here. This is the conjugate base. That it is the acid. All right. So in this example, our conjugate base was blue. Our acid was yellow. So we can take a look here. If the pH is less than the pKa, what is in higher concentration? So if I'm trying to figure out the relationship between these, and I can kind of say like over here, what's going to happen. So let's say we're dealing with the difference between these two. It's 1, meaning like I subtract out pKa minus the pH. It should be something that is dealing with 1. So we could have the concentration of A minus over the concentration of HA is going to be less than that 1. That means that you're going to have a much greater denominator than you are a numerator. Hence, your concentration of your acid is greater than the concentration of your conjugate base. And in this case, if you have a greater concentration of acid, it's going to be yellow. On the other hand, when you are looking at your pH being greater than your pKa, we're going to take a look at our concentration of A minus over the concentration of HA to be greater than 1. So your concentration of HA is less than the concentration of your A minus because you have a larger numerator than you do denominator. So you have a higher concentration of the deprotonated version, which is blue. All right. So hopefully you guys got at least some pieces and portions of this. Make sure you color in your New York State reference table. Make sure this is all colored in as well. And let me know if you have any questions. Take care. Bye.